In this video, we're going to talk about the remaining three types of indeterminate forms and how to compute the limit when they show up. So these three types are 0 to the 0, infinity to the 0, and 1 to the infinity. We mentioned them in the previous video, but this is just breaking them down a little bit more exactly with what I've written down here. So we have the first where both a function and the thing it's being raised to both go to 0. That's a 0 to the 0 type. You could have f of x going to infinity and g of x that it's being raised to going to 0. That's an infinity to the 0 type. And you could also have f of x going to 1 and g of x going to infinity. And that's a 1 to the infinity type. So what we want to do here is we want to talk about how do we compute limits of these three types of indeterminate forms. All three of them we actually use the same trick on. And so that trick is going to use ln of properties. So this is a trick we have done somewhat before. So what we're going to do is we're looking at f of x to the g of x. So that's the expression we're looking at. Now you might remember that e to the ln of something cancels out. And so this equals e to the ln of f of x to the g of x. Because e to the ln cancels out. But logarithms pull exponents out in front. So this equals e to the g of x times ln of f of x. And that is the main trick that we use to compute these forms. Because notice now that this right here is now a product of two things. We have g of x times ln of f of x. And in fact, what's going to happen, because of what f of x can approach, is this is going to be a 0 times infinity form. And so we have e to a 0 times infinity form, but e is a continuous function, so we can just pull it out of the limit. And so in some sense, we just pull it out of the limit, and then work with g of x times ln of f of x. Now I know this can seem kind of technical, so we are going to do some examples. That is why this is a separate video from the rest, is that it's the same trick, but repeatedly doing this trick is helpful. So first we want to calculate the limit as x goes to 0 from the right of x to the x. Okay, so this is like the most standard possible thing we could ask to compute of this form. Clearly as x goes to 0, x goes to 0. So this is a 0 to the 0 form. Okay, that should be pretty obvious. And so now what we want to do is we want to compute what is happening. And so we're going to go through the process we just mentioned. So this is the limit as x goes to 0 from the right of x to the x, which is the same as the limit as x goes to 0 from the right of e to the ln of x to the x, which equals the limit as x goes to 0 from the right of e to the x ln of x. And now, that was the whole using e to the ln trick, but now is the next part where it's helpful that e is continuous. Because e is continuous, this equals e to the limit as x goes to 0 from the right of x ln of x. Okay, so I just pulled e out of the limit. And so now I really just need to compute the limit as x goes to 0 of x ln of x. And we did that in the previous video. I'm going to do it again just to remind you of how it works though. So when compute the limit as x goes to 0 from the right of x ln of x, this equals the limit as x goes to 0 from the right of ln of x divided by 1 over x. So remember 0 times infinity forms are the ones where we take f divided by 1 over g, or g divided by 1 over f. So that's all I did here. Now we apply L'Hopital's rule here. So the limit as x goes to 0 from the right, the derivative of ln of x is 1 over x. The derivative of 1 over x is negative 1 over x squared. And so this then becomes the limit as x goes to 0 from the right of 1 over x times negative x squared So we have the limit as x goes to 0 from the right of negative x, which is 0. So we got 0 in this limit. But remember, that wasn't actually the limit we cared about. That was only part of it. We computed the exponent. And so the actual answer is then going to be e to the 0, which is 1. And this piece right here is the most missed part of this whole process. Remember, after you compute the limit, you take e to that power. That's why it's helpful to actually write e to the ln and do all of this work that I did up here in orange. So you can remember, okay, it's e to that power. Okay, but that same process is the same thing we do over and over again. Okay, and so we are going to do another example of this, but it is the same process as what we just saw. So next example we're going to look at is the limit as x goes to 0 from the right of 1 plus sine of 4x to the cotangent of x. Okay, so this might look a little complicated, so let's actually talk about the pieces for a second. So we have the limit as x goes to 0 from the right of 1 plus sine of 4x. Well, sine of 4x is just going to go to 0 as x goes to 0 because sine goes to 0. So this whole thing goes to 1. The limit as x goes to 0 from the right of cotangent of x. Well, cotangent is just cosine over sine. So this is the limit as x goes to 0 from the right of cosine over sine. Cosine is going to go towards 1, sine goes to 0, so this whole expression goes to infinity. So this is going to be a 1 to the infinity form. So we have a 1 to the infinity form here, so we're going to use L'Hopital's rule to figure it out using our e to the ln trick. So we rewrite this as the limit as x goes to 0 from the right of 1 plus sine of 4x to the cotangent of x. This equals the limit as x goes to 0 from the right of e to the ln of 1 plus sine of 4x to the cotangent of x. And now from here, we're going to pull the exponent down. So this becomes the limit as x goes to 0 from the right of e to the cotangent of x times ln of 1 plus sine of 4x. So we've just pulled our exponent down in front. And so from here now, we pull our e to the x out. So this is going to be e to the limit as x goes to 0 from the right of cotangent of x times ln of 1 plus sine of 4x. Okay, so all of that is just the e to the ln trick. And so from here, we just need to compute that limit that we're raising e to the power of. So we have the limit as x goes to 0 from the right of cotangent of x times ln of 1 plus sine of 4x. Now remember, cotangent goes to infinity, and then 1 plus sine of 4x goes to 1, so ln of 1 is 0. So this is a 0 times infinity form. But cotangent is the same as 1 over tangent. And so we're just going to literally write this using that fact. So this is the limit as x goes to 0 from the right of ln of 1 plus sine of 4x divided by tangent of x. Okay, and so from here, this is now going to be a 0 over 0 form, because we flipped the thing going to infinity. And so we're going to use L'Hopital's rule here. So the derivative of ln of 1 plus sine of 4x is going to be, first we have the limit as x goes to 0. Then we're going to have 1 over 1 plus sine of 4x times the derivative of 1 plus sine of 4x. So that's using the chain rule on ln of 1 plus sine of 4x. And then we're dividing by the derivative of tangent, which is secant squared. So this becomes the limit as x goes to 0 from the right of 4 cosine of 4x divided by 1 plus 4 sine of 4x divided by secant squared of x. Okay, and so this just comes from the fact the derivative of 1 plus sine of 4x using the chain rule. The derivative of 1 is 0, the derivative of sine is cosine, so we get cosine of 4x times the derivative of 4x, which is 4. So that's where we got our 4 cosine of 4x divided by 1 plus sine of 4x. Now at this point, this looks pretty complicated, but let's actually try plugging things in, because as it turns out, that works. So if we plug in 0, we're going to get 4 cosine of 0 divided by 1 plus 4 sine of 0 divided by secant squared of 0. Well, cosine of 0 is 1, so this is 4 divided by 1 plus 0, which is just 1. And then secant squared is the same as 1 over cosine squared. So this is 1 over cosine of 0, which is 1 over 1. So that whole expression is just 4. So we got 4 out of this. But remember, it was e to that thing. And so our final answer is going to be e to the 4th. And so we were able to compute this limit then using this fact. Now let's look at one more example. And so we want to find the limit. So x goes to 0 of 1 over x to the x. So 1 over x is going to go to infinity. X is going to go to 0. So this is clearly an infinity to the 0 form. So we're going to do our trick from before. So we have the limit. So x goes to 0 of 1 over x. I'm going to put a plus on this. 1 over x to the x. So the limit as x goes to 0 from the right. And in this case, this is going to be e to the ln of 1 over x to the x. So the limit as x goes to infinity from the right of e to the x ln of 1 over x. And I probably should specify, the reason why I put the plus on it is so I'm not plugging negatives into the ln right here when I'm doing ln of 1 over x. As x goes 0 from the right, this is going to be ln of infinity, essentially, which is going to infinity. And then 0, x goes to 0, x obviously goes to 0. So this then is equal to e to the ln, e to the limit, I mean, as x goes to 0 from the right, of x ln of 1 over x. So we're going to look at the limit part. So we have the limit as x goes to 0 from the right of x ln of 1 over x, which equals the limit as x goes to 0 from the right of ln of 1 over x divided by 1 over x. Now, the top goes to infinity and the bottom goes to infinity, so this is an infinity over infinity form. So we're going to use L'Hopital's rule here. The limit as x goes to 0 from the right. The derivative of ln of 1 over x is going to be 1 over x times the derivative of 1 over x, which is negative 1 over x squared. Then the derivative is of 1 over x is negative 1 over x squared. Notice those cancel. So we're actually left with the limit as x goes to 0 from the right of 1 over x. So this becomes the limit as x goes to 0 from the right of 1 divided by 1 over x. So this limit as x goes to 0 from the right of just x. So we got out 0 in our limit. But remember, it's e to that power. So with e to that power, we have the limit as x goes to 0 from the right of x ln of 1 over x is 0. So our answer to the limit as x goes to 0 from the right of 1 over x to the x is just e to the 0, which is 1. So we got out 1 from this limit.